Well, good morning, everybody. It's 10 a.m. We'll go ahead and get this going as people are filtering in. My name is Luis. I'm a Long sales engineer here at Long. And today I'm joined by Dan Evans from CRC, Critical Room Control, and he'll be presenting to us on building health and indoor air quality, and specifically focusing in on commercial airflow measurements. So appreciate everybody joining in today, and I'll turn it over to him. Thank you, Dan.
Thank you, Luis. All right, let's get started. So, yeah, with that introduction, what we're talking about today is we want to take the opportunity to talk through some airflow measurement and the impacts that we have knowing our airflow inside of our building. So let's start off today. I'll talk a little bit about building health, indoor air quality, and why we're going to talk about doing airflow measurement. So first one is indoor air quality, and really what it comes out to be is we're really working to create good environments inside of our spaces. And there's something out there, sick building syndrome is one that's used, but it kind of gives us a broad range of things that can exist as we're thinking about our spaces. And so when we look at it, we have some stats up on the screen that just kind of talks about how the spaces that we occupy, day to day, both in our professional lives and both in our personal lives, whether it's a office complex that we go to for our professional lives, or maybe a store or a building that we spend a lot of time in our personal lives. One of the things we talk about is how do we ensure that these spaces are maintaining a level of indoor air quality or level of air quality that is sufficient. And some of the things that ends up being there is, we talk about are there any symptoms that somebody can have by spending a lot of time in a building, most often seen with regards to, probably places of work, right, where we spend, 40, 50, 60 hours a week. And some of the things that we talk about when we talk about indoor air quality and some of the potential causes is going to be things like inadequate ventilation, indoor air pollutants, right? How do we ensure that we're moving those through our space and getting them out? Is there any kind of issue that's coming up with high levels or imbalance of fresh air? So in order to be able to improve our indoor air quality or maintain a high level of indoor air quality, we want to ensure that we understand where our airflow is going. And that'll be one of our topics today with regards to airflow measurement. So along with indoor air quality, talk about kind of an application example. And this one works well because it definitely impacts seasonality. So one of the things that we talk about with regards to a building is ensuring that this building through the course of all seasons and the nature of the year, we can have different things, similar to the stack effect, right? So as we go seasonally between maybe summer and winter, or call it a colder and warmer climates, we'll have different impacts on our building, right? So what happens in the wintertime is we're going to see a lot more airflow coming in on our lower floors because it's going to be more negatively pressurized. And as that colder air enters into our building, we'll have it that will start to heat up and rise through our building and then subsequently try to leave through the upper floors. Well, in the summertime, we're going to see a little bit of a reverse effect, right? We're going to have that colder air higher, and it's going to be entering our building, or warmer air entering our building higher. And then what's going to happen is as it cools, it'll sink through the space and obviously try to leave through our lower floor. So how do we ensure that as we're working through seasonality changing, that we have the right amount of airflow going through our space, right? So we can appropriate, air leakage and ensure that we don't have any kind of uncontrolled infiltration, exfiltration, ensure that we have good energy management of the spaces, right? We don't have a lot of losses based on airflow escaping or airflow moving through a space that isn't as designed or as expected. Pressure imbalance. I mean, that's probably one of our big ones, right? We want to ensure, ideally we keep a building at neutral or, call it slightly positive, but how do we ensure that the space isn't getting negative? And now we are having all that infiltration coming from areas that could get trapped in cavities or in spaces that we're not anticipating the air to come in. And then subsequently, the last one is ventilation rate. We don't want to necessarily over ventilate just as much as we don't want to under ventilate, right? We want to make sure our ventilation rate is good to ensure proper indoor air quality, but certainly doesn't, 4 times is always better than not if we're talking about air changes. But does that mean that it's an appropriate amount of ventilation that could be adding to that increased energy? So With all that, what we want to talk about is how do we measure airflow and ensure that we're getting repeatable, reliable, and accurate information so that when we think through some of these concepts or we try to work through airflow management, we have all the tools necessary that we can validate where we have flow. So I want to introduce a technology to you guys known as passive indirect sensing. This is the technology that CRC uses in all of our commercial airflow measurement. What this technology is, it is nothing active in the airstream and nothing will be directly impacted by the airstream. So what it does, it allows us to become unaffected by airborne particulate or contaminants. We can eliminate drift and fouling and all maintenance that's associated with that to ensure that as we get these airflow stations installed and into the system, we're not spending a lot of time trying to maintain routine maintenance to keep sensors cleaned or probes cleaned so they can keep their accuracy. So some of the features of this technology, is high accuracy and maintenance free, or being able to minimize that interaction, right? So how do we ensure that we're getting a good value, but at the same token, we're not spending a lot of time, 6 months every year, trying to go clean, validate, and add it to a maintenance schedule. Being debris resistant, right? So a lot of airflow that we're going to measure may not be in clean air. Outside air is a prime example. As air enters into our building, we're going to have any outside or environmental contaminant present. We want to look for stability, right? One of the big things with airflow is unless there is a change in the flow rate or the velocity in the system, we want to ensure that nothing is going to be changing with regards to our feedback. Again, contaminant resistant, we want to ensure that all of our sensing ports don't become dirty or something that requires cleaning. And then we talk about being able to do a wide operating range, right? Be able to provide airflow across a large range because we have a lot of units that are varying volume or modulating. So how does it work? So we have a picture of what the airfoil looks like up on the screen. And what happens is air passes into the airfoil. It's going to create its own velocity profile. So as we're looking at this image on your screen coming from right to left, as air hits that airfoil, it's going to split the air in half. And what's going to happen is we're going to create that uniform velocity profile coming across this airfoil. Air traveling across the top of the foil will be moving faster than what's going across the bottom. And subsequently, we will create a static pressure differential. We'll have a lower static on the top side of the airfoil compared to the lower side. And through Bernoulli's principle, we can use that to derive what is the flow coming through the system. So it allows us not to need a lot of develop flow. So our installation gives us more flexibility for getting it into a system because we're just looking for air to cross the airfoil and not have that nice uniform developed flow like we would see in some devices like a pitot. And then from there, we use what's known as dead-ended technology. So we're not going to have our sensor that is outside the airstream. That's why we don't have anything active in the airstream. It's not going to be any kind of flow-through device, right? It's not going to be thermal in nature or some kind of bleed-through sensor where it's going to allow the air to pass from one side of the airfoil through the sensor and then through the other side. We're just going to measure the pressure deflection. It's going to be that dead-ended transducer base. So what it does is allows that no particulate in the airstream is going to entrain itself into the airfoil. So the product that we have in the space is known as our AFW, our airflow wing. And what this product does, and brings in all that passive indirect airfoil and it brings it into our transmitter, allows us to have that high repeatability accuracy with a system that doesn't require the continual cleaning of probes or recalibration of a sensor. So the sensor that we use is one that does not have what's known as drift. So any kind of cumulative or compounding drift would not be something that we're going to have to go in and do the annual recalibration or zeroing of a sensor. Some of the features that we have with regards to our transmitter, it supports multiple airflow stations. So what we can do is from a single transmitter, we can pick up multiple airflows. What I mean by multiple airflows is, let's say we have a mechanical room with a couple air handlers or a package rooftop where we might have an outside air supply and return air. Well, we could measure all three airflows and bring them all back as independent airflows into the transmitter. So alleviating three, call it airflow stations, and bringing it into a single airflow station with three airflow measurements. So great applications when we get into outside air, exhaust air, return air, pretty much anywhere where we're looking to measure air, it's a great for that. And mostly one of the big things is the ability to install and stay contaminant free. So we talk about outside air installations, a big one that pops up all the time, and they say, well, how are we going to be able to mount this thing? So we're looking at hoods and louvers. And one of the things that we have is We know there's a lot of different flavors, shapes, and sizes when it comes into whether it's a air handler itself or just outside air intake coming into a ductwork. But if we have an area where we have a hood or a louver, we have really good mounting abilities that if we can get 6 inches between the damper and the airflow stations or those airfoils, and then depending on the configuration, maybe another 6 inches to a hood, or another 12 inches to a fixed louver, we now have a really good way that we can measure airflow. And so when we talk about placement, this question comes all the time. Well, how do we capture airflow? Just like anything else, as our ductwork increases, we're going to increase the number of airfoil probes that we're going to bring into the system so that we can get a better capture of air as it's moving through the system. So if we're looking at like a single probe, it'd be like a 24 by 24, and we'll bisect the duct and put a probe in there. But as we get to larger duct, we may need to trisect or, get up to 4 probes in a larger, like a 9 foot by 9 foot or 6 foot by 6 foot opening, so we have a better capture of what's happening. Same thing, if we're going to mount vertical, vertical is no change. It's just going to impact which way the airfoil comes into the system. And subsequently, one of the things I always talk about there that's really impactful with this passive indirect sensing technology is the ability to go perpendicular to damper assemblies. So one of the areas that we see most commonly is when we're measuring outside air and we're on the extra side or the inlet side of an outlet or outside air damper. How do we mount it and trying to meet between the blades? This technology allows us to go perpendicular, becomes very, very easy for installation and very forgiving when it comes to the stability then of that flow reading. The next product in our airflow measurement is what we see very commonly in a lot of these systems. We're seeing a lot more fan arrays, right? So we have multiple plenum fans working in unison to try to deliver a higher capacity. And our XF5 product, what it does is brings all the technology, that passive indirect airfoil, but now comes to a transmitter that allows us to do multiple fans and gives us that totalization. So we can do up to 12 fans and we can do it across 2 arrays. So if I have an air handler with 4 supplies and 4 returns, I could bring all that information back to a single XF5, be able to measure my 4 supply fans, my 4 return fans, total them both up. One of the other nice features about this XF5 is we actually have an ability to also bring in outside air. So what we can do is now bring in a outside air station direct into this station and have all 3 on a single transmitter. We could be measuring our return fans, our supply fans, and our outside air with an interface right there in the mechanical room for any maintenance team, and then subsequently have all the backnet integration or hardwire integration to go to the building automation system. So how does the fan inlet installation work? So we use our airfoil, and what we want to do is we mount it across the face of the fan. So one of the big things that we look at there is getting it on the face of the fan. So we can either go, straight across the fan if there's room on the wall or inside the cube, or go diagonal mount, right? We're just looking to ensure that we can mount it so that it doesn't impact the inlet bell of that fan like we have in the image to the left, right? So if you look at that image in the left, we see those blue circles. And one of the things that comes in all of our mounting hardware is an ability to do a standoff. And what it does, it allows us to take that airfoil and come up to 6 inches off the face of that fan so that we're not impacting any of that fan performance. And we've come off the face of that inlet bell. So it allows us to be able to get it installed and not put any performance or degradation against the fan. So very common, we'll see it on the inlet side of a fan. Also, based on that passive indirect technology, this can also be mounted on the inlet side of a backdraft damper. If we have a unit that's already installed or, coming direct from a factory where we're going to have backdraft dampers, one of the things we can do is we can actually mount this on the inlet side of the backdraft damper. If the damper opens, we're measuring flow. If the damper closes because the fan shuts off, we will stop measuring flow. So again, really good technology for flexibility there. And so when we talk about kind of the impacts, when we get into airflow measurement, the 3 big things always pop up: kind of maintenance, sensing range, and flexibility. So when we think about that airflow, one of the big thing for us is from a maintenance side, right? Without having any of that airborne particulate become impacted to the ability to measure flow, we don't have that cleaning requirement. And then subsequently use that dead-ended technology allows us to stay away from that recalibration. A sensing range, we have a large capacity of sensing range. We can go sub 100 feet per minute if we're doing our low flows and like our outside air. And then we go all the way up to 5,000 feet per minute if we have some high velocity systems. And then insulation flexibility, again, without being impacted by airborne particulate, we don't need any pre-filters or anything that we're going to need to make sure we have clean air to measure. Temperature and moisture don't impact because we don't have any kind of active systems in or any active sensors in the system. So with that, I thank everybody for letting me talk to you about our airflow measurement. Again, we start off a little bit. The reason why we're trying to go measure airflow in these spaces is obviously to maintain good indoor air quality, but also maintain good pressurization in our building to ensure that we know where our air is moving. The passive indirect technology that CRC employs as part of our measure airflow product category, and it really allows us to stay away from that airborne particulate and ensure that we don't have a device that requires routine maintenance.
All right. Well, thank you very much, Dan, for sharing that product with us today. And thank you to everybody online for joining us this week. So if you've got any questions or need some additional info on this product or any of the CRC product line that he had there on the final slide, please reach out to your long sales engineer. Join us next week where Mike Soflius will be presenting on Daikin's Precise Line vertical air handler with energy recovery wheels. So hope to see you here again next week. And now for the prizes. This week's prizes are a Meow Wolf gift card, $100, a Coach Tech organizer, and this incredible coffee mug. So thank you, everybody. Stay safe.